So what did we do so far? We kind of took the frequency domain conditions which need to be checked at every omega and things like that. So instead we converted that into LLMI. And anyway, there's a slight difference between checking on the entire complex plane in the right plane versus checking just on the imaginary axis. In certain cases they're one and the same. There's a mathematical equivalence between the two. But at least if we have the LMI satisfied that I presented, then guarantees the frequency domain condition, and then that's how we mostly use it, right? So that in a way takes all these frequency domain conditions and puts right in time domain condition, and we have these LMIs that can be checked very efficiently. It may be iterative, but finally you will get a clear answer, and then there's a simple way of checking whether it's truly satisfied or not, unlike the frequency domain conditions where we have to check at each and every frequency, and then we always have this nagging feeling that that particular condition may be violated on some frequency that we haven't checked. Okay, so that brings us to the part 3 of this lecture, which essentially deals with direct application of Lyapunov function theory to robust stability. So what do we mean by that? And there are again connections to what we've been doing, but in order to understand, I will just spend a little bit of time in terms of understanding how to actually find upper bounds to certain expressions, right? And a lot of times what will happen is basically we'll have expressions, generic expressions symmetrized. You have one part and then plus the symmetric part of it, that AXB plus the transpose of that, so that the overall expression is symmetric. And then we want to bound this. Is there an upper bound that is non-negative definite? Anyway, just a remark that basically if it is scalar, this would have been fairly simple, but if it is not scalar, then we have to be careful. Semi-definiteness is a partial order relationship. What I mean is, if you have two numbers in real line, we know that one of these is true. X is less than y, or x is equal to y, or y is less than x. It's called a full order relationship, whereas in the case of matrices, that's not the case. You can have actually any of these conditions not satisfied, and then B minus A in general need not be anything in terms of semi-definiteness. So such a relationship is called partial order, and that makes things a little bit more complex, not necessarily impossible. Okay, so anyway, so if we look at this particular expression, A minus B transpose times X in the middle, times A minus B transpose greater than or equal to 0, that's like basically, in the scalar case, it's squaring and greater than or equal to 0. Here, by the way, X is positive definite, so you're multiplying something times a positive definite matrix times something, and we are saying it's going to be greater than or equal to 0. So it's like AX square is greater than or equal to 0, right? So if we expand this, we will immediately get basically AXB plus B transpose X A transpose is less than or equal to AXA transpose plus B transpose XB. So what we have to notice is basically the term on the left is what we typically have to deal with, and that's a indefinite expression. But we can actually take take that and then put an upper bound, which is clearly nice non-negative definite expression. And this non-negative definite expression is quite useful in what we're going to see next, right? And just as a remark, basically this is the same thing as if you take the expression 2ab in scalars, we know that it's always less than or equal to a square plus b square, and essentially this is the matrix generalization of that. It's called completing the squares, which has a name and things like that. And then it is quite a trivial observation that we can actually always complete the squares this way, but it's a very useful thing. In many places we can blindly use this expression, and by just taking different a, x, b and things like that, and we keep getting many different upper bounds, right? So let's jump right in. Basically we have this x dot equals a plus b delta a, and here I'm just not even going back to this b delta c kind of a thing, but I'm a little bit more general. And what I'm going to say is, somehow I know to find an expression or a function on this set of positive definite matrices omega of p, and I know that for this particular set of uncertainties, this omega of p is an upper bound in the sense of this partial order relationship semi definiteness. Delta A transpose p plus p delta A is less than or equal to omega p. For now, let's not worry too much about how I know that. Somehow I know, right? And in this particular case, basically all I can conclude therefore is if there exists a p greater than 0 such that A transpose p plus pa plus omega p is less than 0, then the uncertain system is asymptotically stable for all delta belonging to this set delta. Okay. Sorry, this should have been delta sub A. So what this result is doing is basically, if I didn't have delta A, okay, if I had no uncertainty, then essentially the stability condition by now we know it's simply checking for some positive definite matrix so that A transpose P plus PA is less than 0. That's the standard matrix inequality or Lyapunov inequality that we are familiar with. But if we want actually robust stability for a bunch of uncertainties belonging to this set, how do we ensure? Well, we obviously need to be a little bit more careful, and the condition has to be conservative, and that conservative condition is going to come from this omega p, which is an actually upper bound. Somehow it is actually going to bound this delta A part and then produces this, right? So in that sense, it's a very general result, and then the result is straightforward by looking at v of x is equal to x transpose px, and this is what I mean by basically Lyapunov function approach to robust stability. So it's a very fairly straightforward application of Lyapunov function theorem to this linear uncertain system. Okay, but of course, if we don't understand where this omega of p coming from, then all these are useless. Okay, so we will therefore look at bunch of different scenarios. Right, the first scenario is where case 1 where we have this delta A is summation of some perturbation delta I times AI, where AI is known. But what do we know about these delta I's? Delta I's are kind of the set of all delta I's belong to some kind of ellipsoid, right? So that's what we know about this delta I. I could have very well scaled AI so that this becomes actually a sphere, but sometimes it may be easier to have actually this more general ellipsoidal type result. So in this particular case, I'm saying for this particular type of set, we could pick omega of p to be this complicated looking expression, and I'll show you the proof of that in a second. And is this only omega p that satisfies your delta A transpose p plus p delta is less than or equal to omega p? Definitely not. Some of them may be worse in the sense that they are even bigger than omega p guaranteed. Some of them may be indefinite. I mean, you can compare the two, and therefore you may have omega 1 p and omega 2 p, and then one is not necessarily always better than the other ones, and then we have to use both of them, right? So it's not an easy thing to come up with the omega p always, but using our trick of actually completing the squares, we can always find some omega p, and then some of them are better than the others, right? So anyway, the proof goes something like this. If you take this delta A transpose P plus P delta A is equal to summation of this, by using our trick of completing the squares, we can show that each of these expressions within the summation is going to be less than or equal to each of these expressions. But we know that this summation of delta I square by alpha square is less than or equal to 1 based on the fact that they belong to an ellipsoid, and eventually we get this omega of p, right? So what's nice about this particular omega p is basically we have this uncertain system, and we put this omega p, which happens to be linear in p, so we can check this as a feasibility problem in linear matrix inequalities, right? So essentially now the stability problem boils down to checking this expanded version of Lyapunov equation with this additional term omega of p, but it's still linear, so it's relatively simple and straightforward from a computational perspective, right? So this is case number 1. Now the case number 2 is basically where we go back to this B delta C kind of a thing, where delta transpose delta is less than or equal to some non-negative definite matrix n. I could have very well chosen that to be identity, giving back our bounded real lemma, right? So, and for this particular result, this omega p therefore is going to be alpha times p bb transpose p plus alpha inverse c transpose n c, and these alphas provide slightly more variety and things like that. And the proof is again very straightforward, applying this completing squares trick, right? So unlike the previous result, in this particular case omega p happens to be quadratic, so you will end up with a transpose p plus pa plus omega p less than 0 is a quadratic result, right? Quadratic matrix inequality. So in that sense we lost a little bit. The simple linear matrix inequality for checking stability now has become certainly more complex by introducing this quadratic term, but we'll figure out a solution soon enough, right? So let's go to case 3, and case 3 is kind of quite generalized and then combines, like in the positive and bounded real case, this is the generalized positive real condition, so to speak, and then we can actually show that the omega of p is again a quadratic expression in p, and it looks quite complex because of the generality, but beyond that, if you understand the simple case of the previous case and the first case, it's fairly easy to do it, right? In every one of these things, basically we essentially use the completing squares, the trick. That's why I presented that trick as a separate trick, and then every time it works like a charm, and then we get this omega of p, right? So again, the observation is basically we ended up with a stability condition that's quadratic in p. Okay, so while the first result provides a linear matrix inequality, so it's a fairly straightforward thing to do. Quadratic matrix inequalities, on the other hand, are tricky if we want to keep them as quadratic, but luckily there is again a mathematical trick that transforms every quadratic matrix inequality into a linear matrix inequality. Easier said than done in certain cases, but it always works, and that depends on something quite powerful called Schur's complement. And let's state that result. Let y be some arbitrary matrix, and x and z are positive definite, and the sizes are commensurate with one another, right? So that this entire block matrix makes sense. So I'm saying basically the three expressions are equivalent to one another. The first one is positive definiteness of this block matrix x y y star z positive is same thing as looking at x minus y times z inverse y star. So look at the pattern here. I take the x here, which is the right to left corner, then go towards right x minus y times z inverse, and then get back to y star. That has to be positive and z positive, right? So these two conditions put together is equivalent to this one condition that we have there, which is trivial to observe, that actually kind of the third condition, z minus y star x inverse y greater than equal to 0 and x positive, right? And it's a very powerful result, and then it will be a pity if we don't know how to show the result, and then because the triviality of the proof is actually what is attractive, though the result itself is quite powerful. So the result basically boils down to writing this x y y star z as actually a product of something in the middle, which is essentially the two inequalities we have in a diagonal blocks, and a matrix that is multiplying and its transpose on the other side, right? So if this is positive definite, we can know that this is positive definite because what we are multiplying on either side of it, they are invertible, right? And the second part is also can be shown using similar trick, and then I leave that as a homework for you to explore. How can you prove directly from the first inequality to the third inequality that we have, right? So this is one of the most useful tricks that control theorists use to convert quadratic matrix inequalities to LMI, and then we will do that, right? So we will take this case 3 which had this very, let's go back and then see the result there, right? We had this very difficult omega p, which is complicated looking quadratic inequality, and by using this Schur complement trick, essentially it boils down to an LMI, right? So A transpose P plus PA minus C transpose RC, and this B transpose P minus SC, and so on, and you get minus Q and things like that, right? Now, when we actually convert it from quadratic to this linear, the dimension has increased. It's no longer n by n, but it's actually probably double the size of that, depending on the size of Q. But it becomes linear in P, but also linear in QRS, right? So anyway, the fact is basically, by checking this linear matrix inequality, we can check for robust stability for. Yeah, so using this Schur complements trick, we can write this quadratic LMI, quadratic inequality in terms of an LMI. The nice things about this particular LMI is not only linear in P, but it's also linear in QRS, and that actually provides a flexibility. Sometimes, basically, in the scaled small gain theorem, we are looking for the scaled matrices, and that can be useful in actually having linearity in those scales. Okay, so how do we extend this? Well, I'm going to just show you a glimpse of how this extends to nonlinear systems. Again and again, I'm repeating myself that we are showing linear systems because of historical context, but much more if we understand the linear side of things. Actually, nonlinear side of things are relatively straightforward, though specific examples can be very difficult. So replacing this delta A transpose P plus P day A less than equal to gamma omega of P, we will replace that with a similar condition. So we'll have to assume that there is a Lyapunov function, and this inequality is satisfied, and therefore basically somehow instead of V dot being less than 0, we'll have additional this gamma of x. V dot plus gamma of x is less than 0 for all the uncertainties that we have, and then we can guarantee asymptotic stability of the system, right? So in that sense, it's a trivial consequence of the standard Lyapunov's direct method, but by knowing the linear robust stability analysis methods, we can actually state this particular result, right? Now, when we actually look at it carefully, this f of x plus delta f, delta of f, not only like in the linear case, it's typically we assume that it's a constant matrix and things like that. In the nonlinear case, we can directly think of it as actually a nonlinearity. Sometimes it could be a linear matrix times x, right? It could be both. So it can actually include parametric uncertainty and also unmodeled nonlinearity. And the problem of looking at unmodeled nonlinearities is essentially the problem of absolute stability, which we will cover next, right? So, but let me make few observations before going to the next lecture. So, frequency domain conditions apply to linear systems that we know, but in general, it actually allows dynamic uncertainties, and we will think about dynamic uncertainties at a later stage and then kind of consolidate all this information. However, the approach is computationally intensive and incomplete. Incomplete in the sense that not all frequencies can be checked, and then that poses an issue. Then we figured out that basically for every one of these frequency domain conditions, we can use the KYP, the Kalman, Yakubovich, Popov lemma, or its extensions to provide a nice linear matrix inequality condition in the time domain, right? It's a fantastic transition from a very difficult condition in the frequency domain to linear matrix inequality in the time domain, which guarantees certain tests, right? But of course, by viewing this entire problem just purely from Lyapunov function approach, we can actually solve many of these problems using these quadratic matrix inequalities, which can be translated into linear matrix inequalities, right? So the focus in this particular lecture has been on typically constant uncertainties of block structures and then perhaps real parts and things like that. But in reality, a lot of these things become a special case if you actually look at a problem called absolute stability problem, where the uncertainty problem is a nonlinearity. So if you specialize those nonlinearities to the linearities, that gives you robust stability. So it's a transition. I'm trying to increase the complexity in each and every lecture. The first series of lectures is essentially pure static uncertainty coming from some uncertain parameters and things like that. So the next lecture is going to be on the so-called nonlinearity or the absolute stability problem, and all these things can be extended to something called dissipativity theory, which is, all in all a very general problem, right? Thank you.